The human heart sits protected within the skeletal thorax, nested tightly between the lungs and slightly left of center. Functionally, it operates as a continuous, dual-circuit mechanical pump. Its structure drives systemic delivery of nutrients to the body while simultaneously maintaining pulmonary gas exchange in the lungs. To sustain the immense pressure required for this continuous circulation, the heart muscle itself, the myocardium, acts as a high-energy tissue. It demands an uninterrupted supply of freshly oxygenated blood to keep firing. But this creates an immediate physical paradox. The very act of generating that outward pressure, the violent contraction of the ventricular muscle, crushes the delicate blood vessels embedded within its own walls. To understand how the heart survives this mechanical bottleneck, we first have to map the gross routing of its two primary fluid loops, and then examine the unique pressure logic of its private vascular network. The organ's survival requires precise mechanical and vascular coupling. You cannot understand the structural pump without understanding the fuel lines that power it. A septal wall creates 4 chambers. Deoxygenated blood enters the right atrium, flowing through the tricuspid valve into the right ventricle. The ventricle ejects blood into the pulmonary artery to the lungs. Oxygenated blood returns into the left atrium, entering the left ventricle. The left ventricle is the body's primary engine. It generates extreme pressure, forcing oxygenated blood out through the aortic valve, driving the entire systemic loop. Between these stages sit the 4 one-way valves. They do not have their own internal motors. They operate entirely on pressure gradients, snapping shut to prevent retrograde flow during contractions. The result is 2 distinct pumps arranged in series, completely reliant on these structural valves to translate the chaotic squeezing of muscle into continuous forward fluid momentum. While the chambers handle global circulation, the exterior epicardial surface houses the coronary circulation, the heart's dedicated blood supply. The system originates at the aortic root. Left and right coronary arteries branch off the aorta, capturing oxygenated blood leaving the left ventricle. The left main coronary artery divides into the left anterior descending and circumflex artery. Together, they feed the massive left ventricle wall. Simultaneously, the right coronary artery, or RCA, proceeds along the right coronary sulcus to supply the right atrium and right ventricle. On the posterior surface of the heart lies the posterior descending artery, a critical vessel running down the back of the interventricular septum. This specific vessel dictates an anatomical classification known as coronary dominance. Dominance is determined strictly by which main artery connects to and supplies the posterior descending artery. In about 70% of humans, the heart is right dominant, meaning the RCA feeds this posterior vessel. These vessels function as terminal circulation. There is almost no redundant blood supply. If an atheroma slowly obstructs an artery, tiny interconnections called anastomoses might proliferate over time, but a sudden blockage leaves the tissue stranded. With almost no backup flow available, the exact location of a blocked branch precisely dictates which region of the heart muscle will suffocate and die. This brings us back to the mechanical paradox. The left ventricle must contract with extreme force to push blood through the body, but that same pressure compresses the subendocardial vessels embedded deep inside. We isolate the hemodynamics of ventricular systole, the active contraction haze. During systole, high intramural pressure pinches the vessels shut, and blood flow to the inner myocardium drops to 0. The system recovers during ventricular diastole, when the muscle relaxes and chamber pressure drops. As the heart relaxes, the aorta recoils. This snaps the aortic valve shut, forcing blood backward toward the coronary sinuses. Released from systole, the subendocardial vessels spring open, allowing backflow to rush in and perfuse the deep tissue. The only exception is the right side of the heart. Because right ventricular pressure is significantly lower than systemic blood pressure, flow in the right coronary artery never fully stops during contraction. To survive this intermittent pulsing of fuel, the coronary arteries chemically auto-regulate. They dilate or constrict in real time to match the exact oxygen demands of the tissue. The heart is the only organ in the body that feeds itself primarily while it rests. Any condition that elevates heart rate and shortens the diastolic window inherently limits the heart's ability to receive oxygen. We can see exactly where the exterior vascular network dictates internal mechanical function by examining the papillary muscles. These specialized muscles emerge from the ventricular wall, acting as physical anchors for the mitral and tricuspid valves, connecting via string-like tendons called the chordae tendineae. When the ventricle contracts, the papillary muscles pull tightly on these tendons. This holds the valve flaps firmly closed, preventing them from blowing backward into the atria under the extreme fluid pressure. The anterolateral papillary muscle usually receives a dual blood supply from both the LAD and the circumflex arteries. This redundancy makes it highly resistant to oxygen starvation or ischemia. The posteromedial papillary muscle, however, has a critical vulnerability. It typically relies entirely on a single vessel for its blood, the posterior descending artery. If a blockage, like an atheroma, forms in the PDA, it immediately deprives that specific posteromedial muscle of oxygen. Left without fuel, the ischemic muscle becomes paralyzed. During the next ventricular contraction, it fails to brace its section of the mitral valve. The fluid seal breaks. This causes mitral regurgitation, where pressurized blood flows violently backward into the left atrium instead of exiting the systemic loop. A localized failure in a millimeter-wide coronary artery compromises the structural integrity of the entire systemic pump. The heart's macroscopic mechanical output is entirely bound to the microscopic precision of its vascular supply.